What happened before the break? I was trying to tie a lot of loose ends together. Admittedly, these were very long loose ends, so I really required a lot of attention span. We went into one rabbit hole of defining conformal primaries, some analogs of tensors, but now for conformal transformations rather than for general diffeomorphisms. So we defined a notion of conformal primary fields, which transform in a nice way with certain powers of Jacobians. And the subscripts h and sometimes h bar track the powers of the meromorphic Jacobian and the anti-meromorphic one. And then this conformal primary transformation that we prescribed, we wanted that to come from a commutator with a conserved charge of the conformal transformation. So these two perspectives must match by general QFT wisdom, and it required a bit of art to interpret this commutator in the right way. In particular, since I'm treating these conformal fields as commutative variables. So I'm fully with you if you found it slightly disturbing to have a commutator in here. And the way how these commutators need to be understood throughout that course is in the sense of radial ordering. You take with a plus sign the ordering q on the left, phi on the right, where left and right is simply a statement about the respective radii, that the radius of variables here are larger as long as q is on the left. So the commutator effectively translates into a difference of integration contours. And once you have done a careful job to place all the integration contours in the right radial ordering, then you can roll back to the commutative perspective. Then you can remember that everybody commutes with everybody. So I admit this is a little bit confusing, and I'm not even 100% sure whether I can claim to be 100% rigorous in that. But the rules to read a commutator in this course is to take differences of contour integrals. And with this interpretation of the commutator, we could see that the contour integrals in here spit out the right answer if we impose the following singularity structure. And let's say morally, this sounds like going in the right direction. We want to attain a certain transformation under conformal transformations. And all of the conformal transformations are generated by the energy momentum tensor. So it's probably in lines with what you expect, that it's the behavior of the energy momentum tensor that decides about how a given field transforms. And here, concretely, the transformation properties of the primary field, they are encoded in singular terms, as the conformal primary field phi meets the energy momentum tensor. And such statements about singular terms, this is known as an operator product expansion, in short OPE. This is a particular example, but we will see a lot of OPEs in the rest of the course, or, well, the entire subject of two-dimensional conformal field theory is about such operator product expansions, where you track singular terms in a Laurent series in the displacement Z minus W. So let me try to give you a glimpse of how a more general OPE is structured or to be interpreted. So as a commonality of various OPEs, you will see it's a bit like looking at two operators from a distance. So two operators that are sitting somewhere on the Riemann sphere or Riemann surface, that if you look from the distance, they look like a single operator. Where I only need an insertion at one of the 2 points. So here, this single operator was either that or that. So by single operator, I mean not a product. Of course, there can be several choices of what that single operator is, but they are never appearing multiplied. Yeah, and that single operator is inserted in one of the 2 points, and there is a somewhat asymmetric convention. There are 2 points for choice, where you could pile up all the operators on the right-hand side, and without loss of generality, we single out W and insist that all the insertions happen at W. This is important, because if you were to change your mind here, if you say, I want this to be at Z instead, then you would interfere with the simple pole. I mean, you need Taylor expansion to translate between Z and W, so please pay attention that you get the insertion at W correct and don't put a Z by accident. Okay, and I was informally saying from the distance they look like. The more precise way of saying that, we are tracking the singularities, the short distance singularities, and their residues, they are represented by just a single operator. Yeah, so this is always the disclaimer inside OPEs, that we are only tracking singular terms. Then furthermore, in deriving that OPE here, I was at some point using radial ordering, motivating that by the analogous time ordering in QFT. And strictly speaking, that is only applicable inside correlation functions. And the embarrassing gap here is that I haven't even told you yet what a correlation function is. Believe me, correlation functions will be very important and will also be officially introduced soonish. And let me just say for the moment that OPEs are understood to hold within correlation functions. But, I mean, this is actually the only context that matters in CFT. I mean, the important quantities, say the analogs of observables in CFTs, are those correlation functions. If the OPE holds in each correlation function, i.e. in each important context, maybe I don't need to make much noise about this disclaimer. Only valid within correlation functions. And yeah, Carlo made the nice suggestion that I could use the question and answer session to fill in some of these gaps, to walk you through a 2-point correlation function in more detail, such that I can just drop the result here and refer you to the question and answer session for the intermediate steps and details. Okay, yeah, so these are the general comments on what OPEs are doing. One could go into more detail and classify which operators can appear on the right-hand side, given the expressions on the left-hand side. So you can read a lot more about the general structure, but if you want to know, I can point you to specific sections in the references. Instead of delving deeper into who can appear on the right-hand side, I want to give you a more solid understanding of the bridge between commutators and OPEs. So what we just did was we converted the information of a commutator, namely that one, into the information of an OPE. And next we do the converse. Now I want to show you an example where we know the OPE at the beginning and can reconstruct a commutator from it. So the previous section plus the upcoming one are giving you 2 sides of the equivalence you can get from commutator to OPE and vice versa from OPE back to commutator. So we do the second half now. So more specifically, that commutator which we shall extract from OPE, this is about the, let's say, textbook way of quantizing bosonic strings, or at least when following the typical order of material in textbooks. So when not going into CFT early on, one would see a discussion in an early section of a textbook that we should look at this Laurent expansion or Fourier expansion and promote the coefficients alphas to become operators. So one typically appeals to canonical quantization. It doesn't take long to derive commutators for those Fourier modes from canonical quantization. And I will take the somewhat unconventional path of starting with a two-point function, starting with the OPE, and then reconstructing the commutator from the OPE. So more specifically, we will get this commutator from the OPE of this field. Okay, how can we do this without causing any kind of circular conclusion? Let's keep in mind that partial x was our simplest example of a conformal primary. It has these conformal weights. And its two-point correlation function, which I will derive for you from path integrals a little bit later, you don't even need path integrals to fix its two-point function. You know how this one transforms, and even if you don't know what the angular bracket means, a two-point function should transform in the same way as the fields do. So whatever the two-point function is, it must be a function of z and w that respects the conformal primary behavior. So apply all kinds of conformal transformations to z and w and demand that the expression for it respects that conformal transformation. It turns out both two-point functions and three-point functions are completely fixed in their z-dependence. So aside from a normalization factor imposing that the two-point function transforms covariantly, this is enough to see that its two-point function must be a simple pole. So just by exploring consequences of conformal symmetry, check out behavior under translation, under rescaling, and so on. So I think after 3 of the SL2 transformations, you're already done nailing the two-point function to be this, up to a constant multiple. Okay, and getting the two-point function with a double pole, that also tells you what the mutual singularity is. So read off the OPE from the singularity. Here it's a bit ironic, the entire two-point function is singular, so the OPE is essentially the right-hand side. What we learn from this two-point function is that if these two primary fields approach one another, they look like this double pole here with all the prefactors copy-pasted. And okay, in principle, there should be operators on the right-hand side. So if you violently want to see an operator out there, it's the identity operator, which has, by definition, well, which is one everywhere on the plane. It's purely optional to insert it. You don't need to know about the identity operator. If you want to keep notation simple, you can as well say it's that. Yeah. See later for path integral derivation of the two-point function. My apologies if I'm motivating it very briefly by appealing to conformal symmetry. Good. Here we have an OPE, and let's now find our way back into the commutator of alphas. And I should probably leave these contour games alive and instead work on this board. In order to talk about these alphas, let me give you the contour integral representation. Oops. So we talked about this before. If you have a Laurent series and you want to pick up a particular term in that Laurent series, you have to contour integrate, namely put the full Laurent series into the integrand and then multiply it by a well-calibrated power of z, such that you catch the right mode n. Here we are. And in order to evaluate now our commutator, we again use the radial ordering trick. So we impose once more radial ordering. And let me be a bit more schematic. I mean, there will be double integrals, 1 over z, say coming from the first factor, and 1 over w coming from the second factor. And now there is a plus term, that one left, that one right, and there is a minus term, that one left and that one right. And in both terms, I must insist on radial ordering. So the contribution with a plus sign has z of larger radius than w. And then there is another one where it's the opposite. Okay, so in the first place, the integration to do is we are having in both cases circles. I mean, both the first alpha and the second alpha is defined by a contour integral over a circle. But the difference is who is the outer circle, who is the inner circle. So in the first term, z is the outer circle. In the second term, z is the inner circle. And w is the same vice versa. And we do a very similar contour deformation, very similar to what you see on the very top board. So it's almost literally a copy of that strategy. So what we do is the following. We want that ultimately one of the circles, say for z, winds around the point w. And the only difference to earlier on is now that both of them are integrated. So this is just a minor add-on. So let's say w will get integrated. And then for a fixed w, I think carefully about what I do with z. So once you fix w, then there are two contributions. With the plus sign, z is passing w like that. And with the minus sign, z is passing w like that. So completely analogous to how the circle above emerged, we have at fixed w this integral for z to do. So this is by homotopy related to the difference of the contours over there. And we have not pulled the contour for z across w. So we haven't crossed any forbidden points where poles occur. We have only moved around contours in a zone where Z is holomorphic. Okay, so this is using once more the homotopy invariance. Yeah, then let's use the simplified contour on the right-hand side to actually do the integrals. And both of them are a matter of Cauchy. So that commutator here is, yeah, as I said, let's take W as the outer integral. Yes, we do integrate W in a circle around the origin. And then at a given W, there is now a modified contour integral for Z, which is centered at W. And okay, maybe a little subtlety. Let's just make sure that there is no unpleasant intersection anywhere. Let's say the Z radius is reasonably small. Let me write epsilon to indicate small enough. Yeah, and now, and actually, this circle is really thought to be small because we want to use the OPE. If Z and W are really close together, then only the singular terms in here can contribute. So the idea is that we here plug in the OPE. And yeah, as a next step, we would integrate over W. And it currently looks like this is a double pole, so the contour integral vanishes if it's just about the double pole. But the devil is in the detail. We must rewrite all of the Z's in terms of powers of Z minus W. That is not yet in the form we want. So formally, you are obliged to Taylor expand and then get a Z dependence or a Z minus W dependence like such. Okay, so in truth, there's a little bit of simple pole hidden, namely coming in through the Taylor expansion of Z. And you don't need to look any further than that. Of course, if you were to find a quadruple pole here, then you would need a bit more patience with the Taylor expansion. But for a fixed pole order, you're always done with a finite number of terms. Okay, so like this, the Z integral evaluates to the following. Okay, W is not yet integrated. But yeah, first of all, there is a piece of W integrand from here. And now the more recent add-on to the W integrand is coming from the Taylor expansion of Z to the power M. Now this is an extremely simple integral. This is, yeah, literally the Cauchy formula in its simplest incarnation. It's just telling you, make sure that the overall exponent is minus 1. Make sure that n plus m minus 1 equals to minus 1. So in other words, the sum of m plus n ought to be 0. Okay, this is the second Cauchy that I referred to. Good. This finishes the derivation of the commutator, and we didn't even need to think about what kind of Hilbert space could this animal be acting on. Instead, this is one of these commutators interpreted via radial ordering. And you see that the OPE for dx with dx has the full information to reconstruct the entire commutator. I mean, first time I saw this, I found this a little bit black magic. I'm writing down a single term here, a single power behave term. But it is rich enough that it gives me an infinite by infinite array. For each m and n, I get a commutator out of that. This is how rich that OPE is. So I personally find it more streamlined to write down the OPE, because then I'm not risking to get lost in the many indices and super and subscripts. Good. So this was meant to be an inverse to the earlier appearance of OPE. Earlier on, we started from the commutator and arrived at the OPE. And here we did vice versa, starting from that OPE and arriving at a commutator. And needless to say, this is exactly the result that you get by following the canonical quantization procedure, which I skipped. Yeah, this was meant to illustrate equivalence between OPE methods and commutators. Any questions on this? Okay, then let's look at more general compositions of OPEs, or fields whose OPEs you take. This is about the Wick theorem, and it will lead to a compact derivation of the so-called Virasoro algebra. And this is quite a chaotic section. There will also be momentum eigenstates that we can neatly describe with all the OPE machinery. Yeah, very much British cuisine, how many different ingredients are merged into one pot. Maybe the overarching moral here is, let's now go on harvest mode. Let's take advantage of the fact that we have this powerful tool of OPE in our hands, and let's see what kind of mileage we get. So several applications. So let's start with the first bullet point, Wick theorem. So this is about the question, how does OPE work if you have a composite field? For instance, the energy momentum tensor in its concrete realization for the bosonic string, this was a product of two fields. And of course you have seen before the break, once you have an energy momentum tensor, you should have it meet other fields at W and take OPEs between the energy momentum tensor and fields at different points. And then it's pretty easy to get confused. Whose OPE contractions do I take, and which OPE contractions are absent? I mean, you have seen before that dx has singularities with another dx. And knowing about that, it's pretty dangerous to write two of them next to next. So without any further disclaimers, you might be tempted to replace them by their singularity, which goes like, 1 over 0. So you get a horrible mess if you blindly do OPEs everywhere where you see fields next to each other. And as a warning mechanism, there are these colons. So there is, for composite operators of fields, there are these normal ordering colons. And they instruct to not perform any OPEs among enclosed fields. So here in this particular case, you are not doing, okay, I was told to never write down a wrong formula. I wipe it out, yeah. You're not doing this. All right, and now we want to understand if we insert yet another instance of dx at a different point, how does it play out with this product structure here? Is there a kind of Leibniz rule? Is there some distributivity to OPEs? And well, since I illustrated that OPEs encode commutators, then there will be an echo of how the commutators compose when taking products. There is a distributivity law for commutators. One of them is the Jacobi identity. So the distributivity works as follows. Or you can also call it a Leibniz rule of OPEs. Say here, you want to bring together T with yet another instance of dx. I'm careful to have a new Lorentz index and also careful to have a different position. So, spelling it out, there are two dx's at point z and a third dx of w. And these normal ordering colons tell us which OPEs do I carry out and which OPEs do I better suppress. So I'm not sure whether other authors would share this notation, but let me write it in the following form. Yeah, the idea is to mimic the Leibniz rule of differential calculus. You apply the OPE to one of them while copy-pasting the other. And you sum over all possibilities of doing that. Well, summing over all possibilities of doing that is here fairly easy. In that line, I was OPEing the second insertion. So now in the second line, I do the converse, and I am OPEing the first factor. But then there is still the spectator like that. So whenever in doubt, just count whether there is 3 insertions of x in total. Yeah, and in principle, you could wonder about the third option, to OPE this with that, but as I keep on stressing, normal ordering columns tell you to not do that. Good, we know exactly what that OPE is, so by inserting the result from above, we can be fairly explicit on the right-hand side. So clearly, there will be double poles. And the Lorentz index structure will give Kronecker delta and Minkowski metric. So the only free index in town will go to the x field in the numerator. And okay, in the first place, this OPE has a double pole and nothing else. But as I said, be careful where the operator upstairs is inserted. So you get the other operator here. And this is not the same as W. So in other words, to make sure that everything is evaluated at W, you should write this in a Taylor expansion. And if the job of the OPE is to track every singular term, then you will have to take this subleading fellow along. Because together with the double pole from here, it will still be singular. Okay, so here there is a simple pole, and that collects everything which I can squeeze out of the subleading order in the Taylor expansion. And it turns out if you do this carefully, you will get this with the same coefficient as the first term. So relative factor 1. But is this a surprise? Well, not at all. I mean, we found that this is the simplest example of h equal 1 primary. So you could have skipped the calculation. You could have just written down what is the OPE of t with a conformal primary. So we have just in the pedestrian way reproduced what is expected anyway. So since this is h equal 1 primary, then the right-hand side obtained from mechanical work is as expected. So in other words, we are getting confirmed that distributivity works in the way as used here. So my first motivation for distributivity was to mimic the properties of a commutator, how this one behaves when products are inserted. And the second reward is that it reproduces what you knew anyway about the OPE of X with T. Good. This is actually a simple instance of what I advertised as Wick theorem. So here we had a normal ordered product for one of the incoming states, and then the second one was just a single field. But of course, I could have yet another normal ordered product. So how is the combinatorial game played if there is a normal ordered product on both sides? So this is what the Wick theorem addresses. So if you have an OPE of two general normal ordered products, and by general I even mean in principle it can be a product of 3, 4, 5 and more fields enclosed by the colons. And the prescription to deal with that is maybe I first write down example and then try to put it into words. So suppose you have conformal fields A, B, C, D, which may or may not be primary. Then, okay, the taboo is to contract within A and B or to contract within C and D. But there are nevertheless 4 possibilities that are not taboo. 4 pairings between one of AB with one of CD. So here is a first such pairing. But you do the same with A and B swapped, and furthermore with C and D swapped. And little caveat, if some of them turn out to be fermions, we will encounter conformal primary fields of weight 1/2. Then you may get minus signs. So these minus signs are very easy to determine. If you have ever manipulated a Grassmann variable, if you have ever paid attention to anti-commutativity, then it will be straightforward to get these signs correct. Yeah, so these are 4 terms coming from case where a single OPE contraction is performed. But now, Wick theorem tells you something more. You can also do multiple contractions. Here in that case, the maximum number is of course 4 contractions, because then there is nothing left. But the general logic is to sum over all partial contractions and all full contractions, and usually there are many levels in between. Do between 1 and the maximum number of contractions. So this is what I will try to squeeze into this one line here. The instruction is that you should sum over all pair contractions, but also including the partial pair contractions. By partial, I mean that here you don't touch A and D. Good. Of course, if you want to have the final result for the OPE as written here, make sure that you Taylor expand. But this has nothing to do with the Wick rules. This is just that you shouldn't forget about the fact that A is inserted at Z here. Okay, let me apply this specific 2 + 2 instance, which is spelled out here. Let's now apply this to 2 copies of the energy momentum tensor. So there are now A and B correspond to the fields dx at insertion point z. And imagine you bring this together with a C and D, that is yet another energy momentum tensor. I'm not sure whether I'm supposed to give homework, but if you have some free time, do this exercise for yourself. It's definitely highly instructive. And it's actually one of the most important formula in any two-dimensional CFT lecture. What do you get when you OPE the energy momentum tensor with itself? So there are for sure these double OPEs, which means you have a product of this double pole obtained for dx contracted with dx. Yeah, both pair contractions have a double pole by themselves, and hence you arrive at the overall denominator c minus w to the fourth. So this term is clearly the fault of that second line here. And then there is the first line, which gives partial pair contractions. So the structure is along the lines of, double pole. And upstairs are going to be two dx's. These two dx's are coming from AD. But, as I said before, A is at the wrong place. So you still need to do a little bit of Taylor expansion to make sure that all the insertions appear at W and not at Z. Yeah, so whatever the term here on the double pole is, it will bleed into the single pole upon Taylor expansion of that field A here. And if you do all the combinatorics carefully, you find that there's a relative factor of 2 between the energy momentum tensor itself in the double pole and its derivative in the subleading term coming from Taylor expansion. Okay, that formula serves many, many purposes, apart from keeping you busy with the mini homework. It, for instance, illustrates that T is not a conformal primary. If it was a conformal primary, then double pole would the highest it ever gets in the singularity structure. But given that there is this quadruple pole, well, this is clearly a violation of that primary transformation law. So what we can read off, T of C is not conformal primary. I mean, from the double pole, you could be tempted to say, yeah, I can see H equal 2, but just don't call it primary in view of this quadruple pole. Instead, one can refer to it as a quasi-conformal primary of weight 2. Then you preserve the information about this factor of 2, and the prefix quasi admits that there can be additional terms. Yeah, and perhaps I should connect that with the original definition of a conformal primary. They were introduced for the sake of their nice conformal transformation property. So for instance, the map from the cylinder to the plane is transforming primaries in a controlled way. So what about the energy momentum tensor, which is not a conformal primary? Well, you can, of course, transform it from the cylinder to the plane, but in one way or another, this quadruple pole will bite you and give you an extra term. So it's quite a computation to work out the detailed fingerprints of that term. So let me just state how it works. If you transform energy momentum tensor between cylinder and plane, you get one term, which is some sort of the expected one, is squaring the zetas that the individual factors of dx will pick up. But here is the fingerprint of the quadruple term. There is something like a shift of additive constant. And that is sometimes referred to as a 0-point energy. mean, there is a long and tedious discussion of zero-point energies when one does the canonical quantization. There will be every now and then a moment where you pick up a normal ordering constant, and these normal ordering constants, they come in the guise of a divergent series. So they effectively capture, maybe you were already looking forward to the moment where in a string theory course you see this evaluation of a horribly divergent series. So the left-hand side is what you get in intermediate steps of canonical quantization calculations. Maybe you get appeased by the lecturer's comment that this is just a shift in overall energy. And, well, there is no meaning to an overall energy, only relative energies will be seen. But at any rate, there will be a moment where you are asked to swallow this evaluation of a divergent series. And if you're uneasy about that, do conformal field theory and pick up the net effect of the divergent series through the transformation law of T when you go from the cylinder to the plane. Yeah, so either way is fine. You arrive at the same results. So this anomalous transformation law of the energy momentum tensor has the information about the regularized value of this divergent sum. And of course, one can do this in a mathematically tidy way, introducing the so-called Riemann-Zeta function and studying its analytic continuation. So it's doing effectively the zeta function regularization of this infinite series. Good. This is one of the things I wanted to extract of that transformation of T. And of course, another neat information is here in the term that you expected. This is to justify why the mode expansion on the plane takes the following form. Maybe I didn't really comment on it, but if you write down the Laurent expansions of various fields, then there is usually an offset in the exponent here. So we had an offset -1 in case of dx, and we now have an offset -2. Okay, maybe not a surprise, since it's essentially a normal ordered square of dx. And more generally, if you do this for a primary of weight h, you have a -h here, and even for a quasi-primary, this rule goes through. Okay, this is still capturing the primary part of the OPE, but let me comment more about the non-primary term. We were evaluating it in a particular CFT with a particular realization of T, but also in a more general CFT, which may have nothing to do with the bosonic string. It's a generic feature of two-dimensional CFTs that the energy momentum tensor is not a primary and it fails to be a primary by a quadruple pole. So hence, the residue of that quadruple pole got a nickname on its own right, namely, in a general two-dimensional CFT, you write the residue of that quadruple pole as C/2, where C is the central charge. Yeah, so this is one of the key characteristics of a conformal field theory. It's a central charge. So when we later on look at ghosts or worldsheet spinners and their alike, one of the major questions is, what is their contribution to the central charge? And well, in our case, I completely missed to comment on it, you will contract the Lorentz indices as you evaluate the quadruple pole residue, and at some point you self-contract the Kronecker delta, giving you d, the number of space-time dimensions. So here, in case of the free boson in these space-time dimensions, the central charge contribution from all the x mu's is equal to d, the number of space-time dimensions.
Every quasi-primary that's shifted by the same central charge?
Okay. So it depends on how you violate the conformal primary law. There's also a case where you have a triple pole. You can miss the conformal primary transformation law in different ways. And then a triple pole would have different types of fingerprints.
So the central charge is specific to the N-.
Absolutely, absolutely, yes. Central charge is only defined for what happens in T with T. Okay, then we have settled the general name for C. We have obtained this corollary of the transformation law cylinder plane. Then it's time for the Virasoro algebra. Is it okay if I plan to close at 45? Okay. This mode expansion here, or Laurent expansion, this provocates to do a contour integral representation for L, and that will indeed be the key to derive the Virasoro algebra. I mean, these L's, well, they already showed up in the first lecture as to the Fourier modes of the constraints that need to be imposed. And I dodged a direct discussion of how you impose the constraints at a quantum level. But this CFT machinery is doing the quantization for you. So now these L's can be really viewed as the quantum versions of our classical constraints from lecture number 1. And they do have a neat contour integral representation. Well, that same trick as applied to the alphas before. So once more, you take the complete Laurent series and integrate it against an opportune power of Z. And that can be used to derive the Virasoro algebra for these L's from the OPE that you just saw. So we repeat the exercise done in the previous section, but now it's not about the OPE of dx with dx, but it's about the OPE of t with t. You can follow exactly the same tricks as seen for the alphas. The only difference is that you may need to Taylor expand a little bit more, but there is no conceptually new idea. So if you repeat that calculation, replace both L's in this commutator by their contour integral representation, rearrange the integration contours, and apply Cauchy twice, then you can pick up the Virasoro algebra. You find on the right-hand side a first term that you have already seen. So this is something that showed up as the Witt algebra earlier this morning. Up to here, it seems like the little l are following the Witt algebra of the little l's, which were the differential operators to realize infinitesimal conformal transformation. But it doesn't stop here. There is that quadruple pole with an identity operator upstairs. I mean, seeing the identity operator in the OPE gives rise to expect a term which is not L valued, a term which is just a constant. And it is indeed something proportional to the central charge. And the detailed prefactor, you will figure it out if you do the detailed Taylor expansions yourself that are required to apply the Cauchy formula. Okay, so since this is just a scalar, it's referred to as a central term. I mean, in Lie algebra lingo, a central term commutes with everything. So this is not L valued, and well, it's an extension of a simpler algebra that you have seen before. So this means that that extra term proportional to C is the so-called central extension. Of the earlier Witt algebra. Yeah, so you can really view it as a quantum feature in passing from the classical description, say, of the bosonic string now to its quantized version. And I will point out further facets of C, like being eventually a conformal anomaly in a later lecture. So it's really important to keep that term along. Don't discard it just because it commutes with everybody. That's what I wanted to say. Okay, I would suggest you, if you have free time, to also do the intermediate steps for yourself. It's probably a very nice way to really internalize all these contour deformation techniques. By the way, this factor here, it's such that it drops out for m equal 0, 1, and minus 1. There's still a subalgebra, L0, L plus minus 1, that don't feel the central extension. And you saw before, the safety zone of that subalgebra that effectively furnishes an SL2C. So this is the total of 6 generators that you would naively expect if you extrapolate from higher dimensions. But the new features intrinsic to 2 dimensions and only there, this is encoded in the generators with m and n bigger than 1 or smaller than minus 1, and these are the ones that feel the central charge. Good. This chaotic headline of this section also had plane waves in it, or momentum eigenstates. Yeah, so this is yet another application of Wick. Oops. Plane waves, aka momentum eigenstates. So here I want to give you yet another example of a conformal primary. It's an exponential of the free boson X. A normal ordered exponential to indicate, well, it's tempting to series expand the exponential, and then you're in the same trap as before. You have multiple fields on the same point, and it's important to not perform any OPEs among the coincident fields. So this exponential can be read as this infinite series expansion where all the X fields are at the same point and normal ordered. Okay, maybe out of intuition of a QFT practitioner, in order to describe particles, it's useful to classify them by momentum. It's useful to aim for momentum eigenstates. And in all your QFT courses, there were these plane waves where X was just a space-time coordinate. And now we copy-paste the notion of plane wave, but now X has a slightly different meaning. Now X is a key player inside that conformal field theory. But X itself, without the Z derivative, is not at all a primary field. It actually has a logarithmic two-point function, as you will see shortly. So undifferentiated X's are tricky. But in the moment that you exponentiate them, they get considerably nicer properties. So nice property number 1, eigenstate of the momentum operator. The momentum operator is essentially the alpha 0, and this in turn is a contour integral with only del x inserted. So to evaluate the momentum operator, you need to know how these two are OPEing with one another. So the task is to evaluate this OPE, and that's why I'm framing this as an application of the Wick theorem. So you know how dx OPE contracts with one of these fields, and now you do this, well, infinitely many times, expanding out the exponential and doing the Wick rule order by order. And what you find, order by order in the exponential, well, you effectively eat up one of the x's here. And then the associated momentum is no longer contracted against the x. That's why you really get the momentum vector up front. And it's a simple pole because there's only one operator at z, not a second one. You can only do one contraction, but not more than that. So it won't get any more singular than that. Okay, so this is consequence of Wick, where one of the products can be arbitrarily long and the other, one of the factors can be an arbitrarily long product and the first factor is short. Okay, and knowing this OPE, we are prepared to evaluate the momentum operator. So action of the momentum operator is written like one of these commutators encoding a contour integral. So as you can see, it's getting repetitive. I keep on doing the same kinds of contour integrals. And here, the integrand is on the nose involving the OPE I just wrote down. So that contour integral will pick up the residue of the simple pole, and here it is on the silver plate. So you can therefore check easily that the result is indeed the momentum operator is diagonal. It spits out eigenvalue p mu, or whatever you decided to put into the exponent to contract x. Okay, and the last thing I want to say about these plane waves is that they are in fact conformal primaries. They are not only nice with respect to the momentum operator, but also nice with respect to the energy momentum tensor. And at the end of the day, this is yet another application of Wick, where this time one of the factors is a twofold normal ordered product, and the other one an unbounded one. So, good news, these plane waves are conformal primaries. Namely, after fireworks of using Wick, there will be, well, there are now two dx's in there, so you can do up to two contractions, each one giving a simple pole, so the pair contractions give rise to a double pole. And now the residue is, well, you will eliminate two of the x's in that series expansion. So now there are two unattended momenta p, and these unattended momenta will self-contract in their Lorentz index. This is how one roughly finds that. Okay, and then when carefully dealing with the simple poles, namely the partial contractions, one finds this one. And good news, this is exactly what you expect for the OPE of a conformal primary. And yeah, compare it with the original definition. We started out defining a conformal primary by its transformation law, when you perform a conformal transformation with z. I have no clue how I would do this to that exponential. But now we are learning about its conformal properties with the backdoor. We can manipulate it at the level of Wick contractions, OPEs, and contour integrals. We can determine the residue of the double pole. We can diagnose conformal weights given by alpha prime p square over 4. And now if we want to, we could deduce from that how does e to the IPX behave if I do a conformal transformation to Z? I have no clue how I would even start doing that without the OPE machinery. And why is it interesting how that thing transforms? Well, we will in the next lecture start by constructing the closed string spectrum. I still owe you the illustration of where, for instance, the graviton appears, or more generally, how to construct the physical states. And for each physical state, we will start with a plane wave and see how we can form a conformal invariant out of a plane wave. And the first thing we need to know before starting to construct a conformal invariant is, how does it actually transform? What is the conformal transformation of the plane wave that we need to compensate with some other decoration? Okay, so that's the reason why I went pretty deep into all these contour integral games, such that the path is clear to next time construct the bosonic string spectrum, or by checking out what kind of conformal invariants can you build with all of these puzzle pieces here. Yeah, then I will in fact close a bit earlier than initially planned. Thanks.